All right, so we're going to take these piece by piece. All right, I am inclined to start with the easiest part first. I don't know about you, but this one looks nice to me. Okay, so let's start off nice and easy with the phi component of this equation first. So let's focus on that little bit. Okay, so this is the expression that we had from before for the phi part of our differential equation. So I'm just going to rearrange this ever so slightly. You may already see where I'm going with this if you remember our previous experiences with these types of equations. So hopefully this little rearrangement here is screaming out to you. That is our favorite HLD-ECC, homogeneous linear differential equation with constant coefficients. Okay, remember we're always excited when we see that because we know what the solutions are to that form of differential equation. Okay, so solutions similar to before when we've seen these types of expressions are going to end up being of the form of our exponential. Okay, remember you could write these as either in your cosine sine version. We're going to stick with the exponential version just because that it's kind of nice to work with in spherical coordinates. Okay. It just is nice and easy. Okay, so here are the solutions to our HLD-ECC up above. Okay, so we have one version where we have positive m values, one version where we take on negative m values. Okay, so now we are in business. All right, so next step is to apply our boundary conditions. So if we think about what our boundary conditions would be for our system, right? So remember we have essentially a particle on a sphere, okay? Or in this case, since we're only working with one dimension of our spherical harmonics here, we can consider this the same as a particle on a ring, okay? Where we've only got that phi component that we're concerned with, okay? So what we want is to have a nice continuous single-valued situation for a function. So that tells us that our phi must be, our phi of phi must equal our phi at phi plus 2 pi. So a full length around our ring would be 2 pi. Okay, so we want to make sure that both ends of our function connect at that starting point and our ending point positions. All right, so let's focus on these boundary conditions. So what this is telling us is that our function at phi plus 2 pi. So just plug that into our solution expression. Must be equal to our function at phi. Okay, and then same for our negative. Okay, so if we have our minus m options, we're going to have the same situation that we need to satisfy. Okay, so we can simplify that. So our what we're saying here essentially is that the e to the plus or minus 2m pi equals 1. Okay, so if we bring the those equations for the positive and negative options together. Okay, so there, all we're doing is getting our constants on one side. So if we divide by a to the m, okay, we'll get 1 on that side, divide by, get our e's on the other side, and divide, we end up with that expression. Okay? All right, so now it's actually easier maybe to picture what's going on here in terms of our limits if we move into the sine-cosine version of this function. Okay, so this is one time where we do want to use that Euler identity. Okay, so looking at our cosine-sine expression here, we can see that this term is going to go to 0. Right, for even values of pi. Remember, m is going to be some kind of integer that we put in there. Okay, so that leaves us with cosine of 2 pi m equal to 1. All right, so the conditions where our cosine 2 pi m equals 1 will be true for values of m equal to 0, plus or minus 1, plus or minus 2, and so on. Okay, so both positive and negative integer values of m will satisfy this expression. Okay, so again, feel free to take a second to pause the video and satisfy yourself that if you plug in these different values for m up here, you will get your cosine equal to 1. So for even values of your even pi values of your cosine, you should get a solution of 1. Okay, so because our constant, our m values, can take on positive and negative values, we can actually simplify all of these expressions. We can collapse them all into one expression, I guess focusing on our original solutions here. So that makes life a little bit nicer. So we get a final, or not quite final, but close to final expression for our phi part of our wave functions of a sub m e to the I m phi, okay, where m again can be 0, plus or minus 1, plus or minus 2, and so on. Okay, so far we now have a complete expression for the phi part of our wave function. Okay, so at this point, all that's left to do is to figure out what a is. Remember, a is a normalization constant of some sort, so we want to find out what that is. So we're just going to normalize our wave function just like we always do. So we want to take the integral of our function, complex conjugate, and times our wave function again. Here our differential volume element is d phi. Okay, we want to set that equal to 1. A couple of things here. Be careful that you put in the correct limits. So the limits on phi are 0 to 2 pi. Okay, those are different than the limits for theta. Theta goes from 0 to pi. So just be careful that you're putting in the correct limits for the variable that you're working with. Okay, the differential volume element for phi is just that d phi. Okay, so still simple there. All right, and then, it gets exciting. I think this is one of our first functions that is actually complex. So our complex conjugate here is actually going to do something for us. All right, so let's plug in our function. So we have, I'm just going to take our limits here. So we have a to the m, a sub m e to the minus I m phi, that's our complex conjugate, times a sub m e to the I m phi d phi equals 1. All right, so here's where you would get in trouble if you did not pay attention to your complex conjugate. If you went on autopilot and just put in your same function, life is not going to work out very nicely for you right now. Okay, so what is nice about this is, remember for our exponential functions here, we just want to add up the exponents when we multiply them together. Okay, so we end up with, so let's take our constants out. So we have am squared, and then we have e to the 0, d phi inside, and that just goes to 1. Okay, so am squared times the integral of just d phi. Okay, so we get a sub m squared times 2 pi minus 0 equals 1. A sub m squared equals 1 over 2 pi. And then that gives us a normalization constant of 1 over the square root of 2 pi. There is our normalization constant. Okay, so then if we want to put everything together, we have a final function of 1 over root 2 pi e to the I m phi. And we are finally done with our phi part of our wave function. Okay, and that was the easy one. All right, so this is essentially the solution to the particle on a ring problem. Okay, you did a homework problem actually earlier in the semester using these wave functions when you were exploring the ortho normality conditions for the first time. Okay, but this is just sort of the one-dimensional motion for the phi component of our particle on a ring. Okay, so we've got half of our spherical harmonic wave functions taken care of, and we'll take a look at the theta part of our spherical harmonics in another video. Okay, so again, particle on a ring here, or just the phi component of our spherical harmonics. So hopefully you found that helpful walking through that, and we'll move on to our theta.